Good afternoon. Welcome to the ICN2 Nanoseminar in Chemistry and Materials. Today, we have the honor to have with us Professor Liberato Manna. Liberato Manna, he did the PhD in chemistry in 2001 from the University of Bari. And he worked at the university in Berkeley, USA, as a visiting student. And then he did the postdoc with Paula Libisatos in the Lawrence Berkeley Laboratory as a postdoctoral fellow until 2003. He was then scientist at the National Nanotechnology Lab in Lecce, and he moved to the Istituto Italiano di Tecnologia in Genova when he became in 2009 director of the Nanochemistry department. Since 2010, he has been also part-time professor at the University of Delft, the Netherlands. And currently, he's also the deputy director of the IIT for the Materials and Nanotechnology program. His research interests are very, very, very broad. And he did a pioneering work in the synthesis and assembly of colloidal nanocrystals, semiconductor nanocrystal. The study included modeling of structural, chemical, and surface transformations in the nanoscale materials. And he did a lot of work, and a very important work, on their study of their applicability in energy, photonics, and electronics. Today, he will do a talk on Halide Perovskite nanocrystal synthesis, the role of the surface and heterostructures. But before Libero, we have with us Sonia Ruiz Raga, who will do a very short introduction talk on the work of perovskites. Sonia did a PhD at the University of Castelló, Jaume I, in 2000. She got the PhD in 2013. Then he moved to Japan and then to Australia to work on perovskite solar cells. And now, this year, he was awarded by a fellowship, La Caixa Junior Leader Fellowship, when she joined the group of Monica Lira at ICN2. So now, Sonia, the virtual floor is yours, and now and later on, Libero. Please, thank you very much. And do not forget to include your questions, to add your questions in the chat. Thank you very much for both.
Thank you, Nels, for the introduction. And thanks, everybody, for attending. I will share my screen now. So, yeah, thanks again, everybody, for attending. I will present my work on back contact electrodes for perovskite solar cells. So, as we know, briefly, perovskite solar cells have reached impressive power conversion efficiencies in the last few years that are approaching the crystalline silicon devices. And despite there is still some room to reach the Shockley quasar limit, the performance is reaching the edge of practical efficiency limits that are given by a number of factors that are causing losses in the photocurrent and photovoltage. This includes material and interfacial optimization to reduce the recombination losses, or engineering the selective contact energetics to achieve higher photovoltages, to name some examples. It has to be noted that all the reported efficiencies for perovskite solar cells in this chart, and the vast majority in the publications, are based on sandwich structure devices. And sandwich structure has an intrinsic loss in the maximum achievable photocurrent that is caused by the parasitic absorption of the glass, the transparent conductive oxide, the FTO, and also the selective contact of choice that are in front of the perovskite film. In addition, the sandwich structure is very sensitive to any defects in the film processing, in a way that any pinhole in the layers or in the perovskite film will short circuit the anode and cathode and cause charge losses by shunt paths. In addition, one of the main attractive properties of perovskite solar cells is that it can be processed at low temperature on flexible substrates. And then the bending of these solar cells makes them even more sensitive to the creation of shunt paths between the sandwich layers. A solution for these two issues would be to have both the electron and the hole selective layers implemented in the back contact in the same side of the cell. Actually, in silicon solar cells, it has been already implemented the back contact configuration that the purpose was to eliminate the shading of the front electrodes. We just need to develop tailor-made back contact electrodes that are adapted to the particularities of perovskite solar cells. So in this talk, I will introduce you some strategies for the fabrication of back contact electrodes for perovskite solar cells, in which we have modified the architecture, but also the selective contact materials. And I will also briefly explain the challenges and limitations of these structures. I will start with the most simple structure for a back contact electrode, that is the interdigitated electrode. To fabricate that, we used a photolithography mask, and then we evaporated a gold layer through it, and we created this interdigitated structure on glass. And because the use of a single photolithography mask, it's almost impossible to evaporate or spatter two different materials for the selective contacts, as we have in typical sandwich configuration. So in order to provide the selectivity to the electrodes, for the charge separation, we modified them with these self-assembled monolayers of these molecules that have very different dipole moments. And this enabled the creation of a work function difference of about 550 millielectron volts. Interestingly, when you make a solar cell, the open circuit voltage of such device matched this value, and the cell could reach almost 2.6% efficiency. But there are some challenges with this configuration. Some of the drawbacks, it's mainly caused by the electrode spacing that it's given by the resolution limit of the photolithography method. We have an electrode spacing of about 6 microns, while the diffusion length in a single crystal perovskite is in the micron range. Therefore, our device, it's very sensitive to the grain size of the polycrystalline thin films. Another issue is the poor defect tolerance of the interdigitated electrodes. If one of the fingers gets scratched, the entire area until the end gets open circuited, and thus it doesn't contribute to the photocurrent generation. A solution to these issues is to make quasi-interdigitated honeycomb structure. With this structure, we minimize the detrimental effects of a scratch, as the carriers can find alternative paths in the hexagonal structure. Also, it enables to reduce considerably the electrode spacing, because we can achieve a minimum distance of 300 nanometers that is given by the thickness of the insulating silicon oxide, and we can still play with the features with the resolution limits of the honeycomb-shaped photoresist photolithography mask. With different honeycomb sizes, we can indeed demonstrate that the smaller the feature, the better. In the photocurrent mapping, in these photocurrent mapping images, we can observe more uniform photocurrent generation for the smaller features. It's also interesting to observe that the greatest photocurrent is achieved at the edges of this hexagonal feature. This is because it has the smallest distance between for carrier transfer to the electron and hole extraction layers. That is given by the thickness of the insulator layer, which is only 300 nanometers. The maximum efficiency we got with this structure, it's 2.6%, and it's higher than the interdigitated reference. However, we see that we have still very low VOC, and this is mainly caused because of the low selectivity of the dipole molecules. So to solve that, we have fabricated another type of the back contact electrode that uses TiO2 and nickel oxide, that are two of the main semiconductors used in the sandwich architectures. For this architecture, the electrode fabrication becomes more complex because we have to spray pyrolysis the TiO2 and then spatter all these other layers, and including nickel metal. And the nickel oxide is formed by oxidizing the nickel metal under heat and ambient air. And because we know that the interdigitated electrodes resolution, it's not enough for our solar cells, we introduced the mesoporous TiO2 layer to balance the charge extraction and reduce the electrode distances. So indeed, we find great improvements with this configuration. Mainly, we can get open circuit voltages over 1 volt. And with the mesoporous TiO2, we can get much greater photocurrent than in the planar TiO2, that it's given by the more uniform photocurrent generation across the electrode compared to the planar device, as we can see in these current and photoluminescence mapping images. The maximum efficiency in the reverse that we could get is 12.3%, which is a record efficiency for back contact perovskite solar cells. Well, for the planar, it's just 6.1%. And we also note that there is a larger hysteresis in this type of devices, and it's probably due to the interfacial interaction between the perovskite and the semiconductors, something that's also happening in the sandwich architectures. So to conclude, the back contact electrode based on the pole field is an effective method that has the advantage of simpler electrode fabrication. But we need to find other molecules with more asymmetric dipole moments to increase the VOCs. And honeycomb quasi-interdigitated structures and embedding mesoporous structures are effective ways to enhance the carrier extraction and improve performances. And also very interesting is that the back contact electrodes provide unique opportunities to study, to do electrochemical in situ studies of perovskite films, because the perovskite is grown on an already made electrode. For example, it could serve to monitor the film formation or exposing the film to solvent vapors or solutions to modify the grain size, ion exchange, etc. And you could monitor IV curves or measure impedance spectroscopy during all these changes. Okay, thanks for your attention. And if you have any questions.
Thank you very much, Sonia, for the nice talk, introductory talk. As Alex reminded in the chat, just have in mind to include and to type your questions and comments to ask Sonia or Libero at the end of the seminar. Now, I think that we can move to Professor Liberato Manna's talk. If you are ready, everything is okay. I think so. So now it's time for Libero, who will present today his talk entitled Halide Perovskite Nanocrystal Synthesis and Optical Properties. Please, Libero, the floor is yours.
Good afternoon to everyone. So perovskites have already been introduced in the previous talks. So in this material, it's very hard to form defects, and the only low energy defects that you can actually form are vacancies. Now, it turns out that compared to the standard semiconductors, as you see in panel B, actually the formation of vacancies leads to traps which are nested in the valence and in the conduction band, and so they are not so detrimental for the optical properties of the materials. Also, because of the formation of polarons in this structure, there is a reduction of the carrier-carrier scattering, so the carriers actually live a very long time, and this is at the base of the high efficiency in solar cells. Now, people have been doing nanocrystals also out of perovskites, in these materials, you can easily tune the optical properties. And these are the first two works which have started this field in 2014, 2015. Now, these are the different materials that we are actually targeting in our group. We do electroluminescent devices, we do solar cells, we do scintillation for detection of X-rays in collaboration with Brovelli in Milan, and we also do luminescent solar concentrators. Now, there are a lot of transformation that you can imagine in perovskite nanocrystals, and this is the reasons why these materials have been so, let's say, interesting for chemists. So, for example, you can imagine to do an ion exchange in these materials to tune the optical band gap, but you can also do, for example, A-side cation exchange. You can exchange, for example, cesium with formamidinium, and you can do also a lot of other chemical transformations. So you can go, for example, from cesium bromide to cesium lead bromide, or to cesium 4 lead bromide 6 to cesium lead bromide by intercalation and de-intercalation of different types of species. So you can also do B-side cation exchange. For example, in cesium lead chloride, you can remove part of the lead and replace it with manganese to obtain a trap emission from these doped systems. This is one example of a transformation that we did a few years ago together with Dmitry Baranov in my group. What we did was to treat cesium 4 lead bromide 6 nanocrystals whose structure is formed by a disconnected octahedra with a polymaleic anhydride, which actually caused a lot of transformations, removal of ligands and expulsion of cesium and bromide out of these nanocrystals, and actually the reorganization of the lattice from cesium 4 lead bromide 6 to cesium lead bromide 3. And the structural transformation is actually guaranteed by the continuation of the cesium cation framework in these two materials. So you get intermediate epitaxial heterostructures. And now what we found out was that these kind of transformations are very common in perovskites. For example, you can go from cesium bromide to cesium lead bromide 3. Again, what rules this transformation is the preservation of the cesium cation sublattice. You can even go, if you see in panel C, from cesium lead bromide 3 to cesium lead 2 bromide 5. And all these transformations, for example, are triggered by the addition of lead bromide to a starting cage of cesium bromide. And you see also that here the transformation and the epitaxial interface is guaranteed by this continuation of the cesium bromide, the cesium cation framework. One important contribution that we gave to the field of perovskite was the use of single precursors like benzoyl halides in this case, which introduced in the synthesis reaction react with the amines and the carboxylic acids in the environment, freeing hydroallylic acid, which act as the source of halide in this system. Why we do this? Because by decoupling the benzoyl halide from the lead precursor, we could work under halide-rich conditions, and this led to the formation of nanocrystals with very high quantum yield and good optical properties. So we could also make methylammonium and formamidinium lead halide nanocrystals. What you see below are films of cesium, methylammonium, and formamidinium lead bromide nanocrystals with very good optical properties, exhibiting low threshold for amplified spontaneous emissions, telling that the optical quality of these films is very high. Now, you can choose different ligands for pacifying the surface of the nanocrystals, but traditionally alkyl ammonium and carboxylates, they can easily protonated or deprotonated, and so they can detach from the surface of the nanocrystal, and this causes high instability of this material. So in the search for more stable ligand, people have been looking, for example, into zwitterions, phosphonic acids, and we did a study with the quaternary ammonium halide. So this material, these ligands, you cannot detach because the positive charge remains constant, and so they remain tightly anchored to the surface of the nanocrystal. So for example, if you start from cesium lead bromide 3 nanocrystals and you replace the native cesium olate ligands with the quaternary ammonium bromide ligand pair, you see that the optical properties of these nanocrystals remain constant in time and close to 100%. What you see in the lower panel of this slide is a synthesis of alloy nanocrystals based on lead and cadmium. And actually, it turns out that if you don't do the ligand exchange and you leave the cesium olate ligands, the blue emitting nanocrystals actually lose their blue color over time because cadmium ions leak out of the crystals, probably due to surface halide vacancies. Whereas if you do a ligand exchange with the quaternary ammonium halide, this does not happen, and so the blue color of the nanocrystal remains, and also the emission from the electroluminescence from LEDs made by these ligand-coated nanocrystals remains stable over time. Now, we also did recently some cool experiments, for example, in growing nanocrystals of cesium lead bromide into mesoporous silica using molten salts. This reaction environment basically seals the pores of the silica and makes these nanocrystals very stable even in aqua regia for months. Okay. Now, with these silica-coated nanocrystals, we could, for example, prepare nanocrystals films emitting white by combining blue LEDs plus nanocrystals emitting red plus standard red phosphors. And here you see two typical applications of this silica-coated nanocrystal. So very bright emission, close to perfect white color. We recently did some improvement in this kind of synthesis of color selective and stable nanocrystals by employing a block copolymer together with some small molecules which improve the compatibility between the nanocrystals and the polymer. So this is a standard LARP synthesis modified with our chemicals. And what happens is that these nanocrystals are encapsulated in a sort of polymer micelle which can turn from the coiled to the globule state depending on the conditions of the solvent. So for example, in a polar solvent, the polymer is in a globule state, so the nanocrystals actually do not communicate with the external environment, and so they cannot exchange ions. So for example, you cannot do anion exchange reactions. In toluene, for example, the polymer is in the coiled state. So in methanol is a global state, in toluene is in the coiled state, and the nanocrystals can communicate with the external environment, and you see that they do anion exchange. So this is another example of exchange from the bromide to the chloride. A precursor, you see in toluene, it happens, in methanol it doesn't happen. This is the case of nanocrystals in methanol, and you see anion exchange is not occurring, but as soon as you are adding toluene, the anion exchange it's actually taking place. Okay, so what you could do is start with the green emitting sample, do all these anion exchange reactions, then dry, precipitate the nanocrystals, actually mix them with the PMMA, you dry them, you ball mill, and you get a very stable powder emitting at 3 different colors, red, green, and blue, and you can actually mix them in the right proportion to get a white emitting powder. So with this white emitting powder, you can make a polymer films. So for example, by mixing this with polyvinyl alcohol and get a white emitting down converting film, which you can deposit on top of UV emitting LED. And you have to also get a long pass filter on the top of it to filter the non-absorbed UV light. And so what we got was the first completely white down converting film based entirely on lead halide perovskites. Now we also did work on different type of materials. So for example, we worked a lot on double perovskites. Okay, so where the lead is replaced by 1 monovalent cation and 1 trivalent cation. A first example of the synthesis is this cesium silver indium chloride nanocrystals. These nanocrystals, as the standard, the bulk materials are poor emitter. The emission is from self-trapped excitons and with a PL quantum yield of just 1.6%, strongly stock shifted from the absorption as it should be for, let's say, a self-trapped exciton type of emission. When we dope with these materials, with the manganese, for example, we could get up to a doping level of 1.5%. Then the matrix as a host, as a sensitizer, the excitation gets transferred to the manganese. And so you get the standard orange-red emission from the manganese due to this internal DD transition of the manganese, which is, of course, very long-lived. So you have a lifetime of milliseconds. And of course, by electron spin resonance, we could demonstrate that the manganese is inside in this material. Now, then we shift to a more complicated system. You see, this is an alloy of it's a double perovskite, but in the B side, there is an alloy of silver and sodium, okay? And in the B3 plus side, so the B1 plus, it's alloy of silver and sodium. B3 plus side, there is a slight doping of bismuth. Why we do this, and of course we can change the ratio of silver to sodium, is because the group of Sargent reported close to 90% PL quantum yield from these nanocrystals. Well, the way it works in this material is that in the pure compositions of silver and sodium, for example, the exciton is completely, the carriers are completely delocalized. But when you introduce a little bit of silver, for example, in a material made of cesium, sodium, indium chloride, and you introduce a little bit of bismuth, then you get electrons localized mainly at this bismuth chloride octahedra, and hole mainly localized at the silver chloride octahedra. And so the recombination is actually due to basically, the emission is due to a local recombination from carriers localized at, let's say, neighboring octahedra. And the efficiency of this emission is, of course, regulated by the ratio of the silver to sodium. Now, the way it works here is that the silver chloride octahedra act as, let's say, electronic confining barriers. So if you have a lot of them, you have a few isolated silver chloride. And if you have too many silver chloride octahedra, on the other hand, the hole gets delocalized and the PL quantum yield goes down. On the other hand, if you have a lot of sodium ions, then you have few emitters because you simply have very few silver chloride octahedra. So it's a balance of these things. But in any case, in our nanocrystal, the PL quantum yield was actually very low, 22%. So the only thing I want to tell you about this slide is that you can change the ratio of sodium to silver, and you change the band gap of the material, as you see on the panel A on the left, basically in the absorption, but the emission is always picked at, let's say, 1.9 eV or so. And this is because the emission is always from localized state, localized on bismuth and silver chloride octahedra. So this is quite insensible to the band gap. Now, what you see in the lower panel, you see that by increasing the amount of sodium, the PR lifetime goes up. And this is telling us that actually sodium chloride octahedra indeed introduce barriers for the excitons to move from one place to the other, and actually removes the less efficient non-radiative pathways. So the more sodium is around, the more the exciton is localized on vicinal bismuth chloride and silver chloride octahedra, and the more is the probability that it can recombine radiatively. But still, there is one point here, and is that the PL quantum yield from this material is much, much lower than that of the bulk, which is close to 80–90%. So we tried to make a different synthesis of nanocrystals of this type of material with different combination of ligands. And it turned out that we can, so first of all, using different alkylamine and alkyl carboxylic acid, by NMR, we could demonstrate that this form a very well intermixed shell on the surface of the nanocrystal, so there is no segregation of the two types of ligands. And the maximum PL quantum yield could be reached by, let's say, a carboxylic acid, which has an alkyl chain of C12, and amine, which has an alkyl chain of C10. And the quantum yield, it's only 37%, okay? So the point is that despite we tried very hard to improve the synthesis of nanocrystals, the PL quantum yield is much lower than in the bulk. So there is something here that is very much different from the standard perovskite nanocrystals, and maybe there is a trap states on the surface. So what we did was to model the surface properties of this material. So we build a model of a nanocrystal, a few nanometers in edge length, completely passivated by cesium chloride to, let's say, simulate a passivation by ligand pairs, by a couple, for example, cesium-olate. Okay, but cesium-olate is too difficult to model. What we see is already that on the top of the valence band, the states are very localized, and these are actually due to chlorine NP orbitals. Okay, the p orbitals of the chloride ions form the top of the valence band. They are already localized state. What we did now, as you see in panel B, we started removing cesium chloride ion pairs, modeling, sort of simulating the removable ligands from the surface of the nanocrystals. And we monitor now you see in this sketch here, we monitor these trap states due to the formation of traps by looking at this chloride ion sitting on top of a silver ion. Okay, when you start removing cesium chloride ion pairs from the vicinity of this ion, you start forming trap states which are deeper than in the fully passivated case. When you start removing more cesium chloride ion pairs, you start forming, for example, in this case, you remove 3 cesium chloride ion pairs, you form very deep trap states. Okay. Instead, you start from a situation where you monitor a chloride ion sitting on top of a silver ion, and the silver ion, because of the d orbitals, are able to delocalize more states. What you see in this case is that when you remove cesium chloride ion pairs, the traps that you form because of this unsaturated chlorine ion are more shallow. Okay, but the overall message here is that unless you have a perfectly surface passivated nanocrystals, and even in that case, you have localized trap states, but unless you have, let's say, a fully surface passivated nanocrystal, you easily form these trap states, which are very detrimental for the optical properties. So this is very much different from the case that I've shown you in the initial slide, where I've said that in perovskites, trap states are very benign because they they are nested within the valence in the conduction band. But here we are not talking about cesium-lead chloride nanocrystals. We are talking about double perovskite nanocrystals. So to make a comparison clearer, I show you the electronic structure, very rough, of a standard perovskite. So B2 here can be lead or can be even zinc or germanium, for example, 2+. And indeed, you see that the p orbitals of the halide ions indeed are very deep in the valence band. And when, let's say, they are sitting, these orbitals are sitting on the surface, they are non-saturated, they form non-bonding orbitals, which are still indeed nested deep in the valence band. Now, in a double perovskite, because of the presence of this B3+ cation, which has a strong nuclear charge, the orbitals, the NP and S orbital of the 3+ cations are very pulled down in energy, and this causes actually the NP orbitals of the halide ions to move very close to the top of the valence band. And so in this case, when this halide NP orbitals on the surface are not passivated, so they're not saturated, they form trap states, which can be shallow, but also very deep. And also notice also the B3+ NP orbitals, which also, when they are non-passivated, non-saturated on the surface, they form deep trap states, as opposed to the B2+ case. So now we thought of looking for a way out of this thing, and we thought that in a standard 3D perovskite, like the double perovskite, the exciton can easily migrate to the surface due to phonon coupling. Okay, all these octahedra are connected, and so exciton phonon coupling is very strong, and this can easily move an exciton close to the surface. On the other hand, in a zero-dimensional system in which the octahedra are completely disconnected from each other, because of this much lower exciton phonon coupling, we reason that excitons formed in the bulk of the nanocrystals will have harder time to migrate to the surface, and so they would probably have nanocrystals of this 0D system would have higher PL quantum yield. So this is what we tried recently. We started from 2 systems. Actually, these are 3 systems. We took two very similar types of double perovskite. In one case was cesium, sodium, indium chloride nanocrystals, and in another case was cesium, potassium, indium chloride nanocrystals. And we doped them with antimony. Okay, so antimony doping with antimony leads again to exciton, self-trapped exciton emission. And we compare this system with the system in which the octahedra are completely disconnected. And this is the case of rubidium-3, indium chloride 6 nanocrystals. So now you have indium chloride nanocrystals, octahedra completely disconnected with each other. And also in this case, we introduced as dopant antimony. Okay, so the TM of the respective nanocrystals are shown below for the case of this low level of dopant of antimony. So in the range of 0.0103% for double perovskite, 1% in the case of the 0D rubidium indium chloride. So what we found out was that invariably in the 0D system, the PL quantum yield is always higher. It's at least twice as high as in the case of the antimony doped double perovskite. And this does not really depend on the level of doping. So you can tune as much as you want the amount of antimony in the 2 systems, but you will always end up with a higher PL quantum yield in the 0D case, which again is somehow supporting our hypothesis that in the 0D, the excitation that is formed in the bulk of the nanocrystal is probably traveling slower to the surface, where it would likely to be killed. It would be likely killed because of these surface halide traps. But of course, this is only an hypothesis for now, and more consistent studies need to be done. Now, in our quest to, let's say, identify new materials in general, we stumbled into this chalco halides. These are nanocrystals of a phase that could never be done before. There is no equivalent in the bulk of lead 4 sulfide 3 bromide 2. There is an equivalent in the case of the iodide, lead 4 sulfide 3 iodide 2, and this is a high pressure phase that can only be made, as I said, in high pressure in the form of microcrystals. So we were able to make these nanocrystals, which apparently are a sort of kinetically trapped metastable structure. These materials, because of the novel crystal structure, could not be indexed to any of the known phases of lead sulfide or lead sulfobromide, which you see here in the central panel C. And so we had to play a lot of tricks to, first of all, figure out their composition. So we did XPS, we did semi-DS, and then we also combined the X-ray diffraction with thermogravimetric analysis to see all the products of the degradation of this material and to quantify them. And we came up indeed to, let's say, a stoichiometry for this material, which is lead 4 sulfide 3 bromide 2. So to figure out the crystal structure of this material, to solve actually, identify the position of the atoms, we had to resort to 3D electron diffraction on a single nanocrystal. This is a very complex and elaborate way of solving crystal structures. And this gave us some tentative ab initio solution. We also did, so this was done with the group of Mauro Gemmi in Pisa. And with the group of Sarabals, we also attempted 3D electron tomography on a single nanocrystal with the atomic resolution, okay? We failed to do this to identify the position of the single atom by STEM tomography because the sample heavily damages during this data acquisition. But indeed, the quality of the sample during the examination and overall the resolution of the technique was enough for us to retrieve the lattice parameters, so to figure out that the lattice is orthorhombic and to find out the parameters of this orthorhombic cell, which actually matched quite nicely with the parameters found by the 3D electron diffraction shown in the top on a single nanocrystal. Now, so by combining 3D electron diffraction and STEM tomography, we could get to a very good guess of what is the structure of this material, what is also the atomic position in the cell. What we did also to get the cell parameters from these two techniques and to feed them into a standard program for ab initio solution, structural solution, starting from X-ray powder diffraction data. Also, in this case, the ab initio solution that we got was very similar to the one by 3D electron diffraction. And when we relaxed both structure by DFT, they basically converge to the same structure, telling us that we are in a good, we were indeed in a very good direction. So we modeled the optical properties of this material, which exhibits an indirect band gap. Okay. So in this material, you have a lead coordinated by a mixture of sulfur and bromide ions. And also, if I'm not wrong, the bromide is in an octahedral coordination. So it's a kind of a weird structure. And also, I have to say, not very much interesting, neither from the optical nor the, let's say, electronic point of view. So we tried, just to give two examples, we tried to make a photodetector out of these materials. We made a film of these nanocrystals. We did the standard ligand exchange. All the treatments that are done in general by the device community. And this photodetector, for example, showed a decent responsivity and detectivity. We also tried to build a solar cell out of it with a very low power conversion efficiency. Okay, so I mean, the material by itself, it's not terribly interesting. But what we were able to do, actually, and this is probably a little bit more interesting, is that we could grow heterostructures in which these chalcoid halides are epitaxially connected to halide perovskite. The way we did was to first prepare clusters, so ultra small nanocrystals of halide perovskites, which we use them as a precursors to grow the perovskite. And we mix them with all the precursors that are needed to enucleate and grow the chalco halide. And it turned out that in this synthesis, the perovskite domain nucleates and grows very fast, but attached to it, a chalco halide domain grows. And you see very little byproduct in this synthesis, just a tiny amount of isolated halide perovskite nanocrystals. So you see in this panel B and C, the nice epitaxial interfaces. The brighter domain is the chalco halide domain, which is very rich in lead. That's why you see this very strong scattering of electrons in the HUD image. The optical properties of these heterostructures, it's basically in absorption is a combination of the absorption spectrum, the broad absorption spectrum of the chalco halide and the sharp excitonic peaks of the perovskite. And the PL that you see from these materials, it's actually, and you will see later, it's mainly attributed to the remaining nanocrystals, perovskite nanocrystals that are not part of a heterostructure in solution. And this is by comparison, a standard optical absorption and PL spectra of solution of standalone cesium lead bromide nanocrystals. Now, we did extensive, let's say, high-level electron microscopy analysis thanks to the group of Sarabals. So you see, for example, in panel A, a single heterostructure. You see the very sharp epitaxial interface between the two domains, which is magnified in B, and in C, you see an atomistic model of the interface. In the panels from D to G, what we're doing here is labeling different atomic columns in the samples with different, let's say, in each panel, we are labeling a given type of atomic column. So in panel D, we are labeling for example, we're identifying the lead bromide columns. In panel E, the cesium columns, and so on and so forth. With the message that I want to convey from this slide is just that this is really truly an epitaxial interface, and we know very well the relationships between the two domains, to the level that we could really build atomistic models of these materials, and indeed demonstrate that it could nicely match on top of each other. So, for example, on the left, you see a model of chalco bromide nanocrystals. Here in the central part, you see the atomistic model of the cesium lead bromide. You can fit, for example, this sphere. You cut this sphere in half, you get an hemisphere, and then you position on the top of this cube, and the matching is very nice. You can actually see this matching from on the right side of this slide. You see here what we are showing here. It's only the lead columns here. This is a side view, and this is a top view of actually these two planes here. So this plane here belongs to the chalco halide, definitely. And then you see this plane here. This plane here can belong either to the chalco halide or to the perovskite. There is a perfect matching here. Okay, so you can just glue one on top of the other. Now, I'll spare you all the optical characterization that we did on this material. It's actually not very interesting. Basically, this heterostructure completely quenches the emission from the halide perovskite. And what we saw was that the residual PL that we get from the heterostructure, and in this panel is the heterostructures spectra are in orange. So very low PL, more or less at the same position than the PL from a solution of isolated cesium lead bromide nanocrystals. Here you see the PL lifetime from the green emission from the heterostructure. It's basically the same as the lifetime, so that the PL decay curve is the same as from a standard solution of cesium lead bromide. So telling that the weak green PL that we are observing in this sample is just from isolated nanocrystals of cesium lead bromide. If you make isolated chalco halide nanocrystals, then they are not emitting at room temperature. You have to go to cryogenic temperature, and then you start seeing a bright emission and more or less 1.8 EV. Okay, so these are all fingered, this very broad absorption, stock shifted emission only seen at low temperature. These are all fingerprints of emission from indirect band gap material. When you combine these two domains together in the heterostructure, what you see is actually that the emission from the heterostructure, it's redshifted compared to the emission from the. This is done at low temperature, so we are seeing in the we are seeing this close, to the near infrared region. It's redshifted compared to that of the chalco halide, and you basically get the same emission regardless of whether you are exciting the heterostructure in the perovskite or in the chalco halide domain. And so the model that we have here is that, first of all, there is a quasi-top to band alignment between these two domains. This we assessed by calculations. But then, even if there is a perfect epitaxial interface between the two materials, there is a lot of trap states forming at the interface. And when you photoexcite this heterostructure, carriers are rapidly, let's say, migrating to the interface, and they recombine mostly non-radiatively and partially radiatively from these trap states. So that's why you see this stock shift emission. Now, you take this heterostructure, and what you can do is, for example, try to do an anion exchange. Okay, so you try to replace the bromide ions with either chloride or iodide ions. It turns out you can do this, but the anion exchange reaction, it's only taking place in the perovskite domain. So basically, in the chalco halide domain, the ions are completely frozen. And so you end up with two novel type of heterostructures, which are also perfectly epitaxial. Okay, now, again, very interesting, but not much interesting, maybe from the applicative point of view. If only for this aspect, which I'm showing in this slide. So if you take a standard cesium lead iodide nanocrystal, you know that a solution or a film of these nanocrystals will quickly change color in a matter of days, because this perovskite phase for the cesium lead iodide is very unstable. So you observe quickly a transition to the non-perovskite phase, which is formed by these one-dimensional channels of connected octahedra. Okay. On the other hand, if you prepare a solution or a film of nanocrystals of perovskite, so these of course we are monitoring X-ray powder diffraction of a film of perovskites of heterostructures over weeks. What you see is that the perovskite phase remains stable, and this is due to the fact that the chalco halide, by being epitaxially connected to the perovskite phase, glues this phase, and it prevents a transition to the perovskite phase. Okay. Now, as the last example of the use of this, what we can do with this combination of materials, I'm showing you a sort of a possibility of using these nanocrystals of the nanocrystals of perovskite as a sacrificial templates for the synthesis of chalco halide, for the phase selective synthesis of chalco halide. Now, we are moving now to the to the chloride-based systems, and so we are making chalco chloride nanocrystals, lead sulfide chloride. When you try to synthesize these nanocrystals in solution, in the absence of clusters of perovskites, you end up with the monoclinic phase of cesium of lead sulfide chloride with this stoichiometry, lead 3 sulfide 2 chloride 2. On the other hand, if you do the same synthesis in the presence of cesium lead chloride nanocrystals, you end up with an heterostructure, okay? And the crystal phase and the stoichiometry of the chalco halide domain is completely different from that of the chalcoylide, which is homogeneously nucleated in solution. This is a monoclinic phase. This is an orthorhombic phase, and also different stoichiometry, because it has to match epitaxially the perovskite. Okay, but now what you can do is take this heterostructure, completely dissolve the perovskite domain, and end up with the chalcoylide domain, okay, in the form of isolated nanocrystals in an orthorhombic phase, which you couldn't get by direct synthesis. So what we are showing here is the exploitation of the lability of the perovskite to act as a sort of template for the synthesis of phase selective synthesis of material. And then you can get rid of the perovskite by simply pouring into highly polar solvent. So by this, I think I'm just also going over my time. I thank all these people who have made all this project possible, and also the funding agency, and all of you for the attention.
Thank you very much, Libero, for the amazing talk. Honestly, I have to say that every time that I'm seeing your talk with a lot of material, a lot of different combination, a lot of different structural characterization, it is completely amazing. I think that just congratulate you for the nice talk. And I think that we have some questions from the audience. So we have one question from Pinzeng Zhang. I think that this question is from the very beginning of your talk, just to contextualize you. And she's asking us, you would like to ask if is the intermediate heterostructure between cesium-4 lead, bromide 6, cesium lead, bromide 3 thermodynamically stable or equally unstable as cesium, bromide, cesium, lead, bromide 3?
It is stable. It actually is stable. You can cook this heterostructure to maybe 200 degrees, and they are okay. If you go over, of course, then it's not stable anymore, because the chalco halide domain tends to decompose to lead sulfide and a stable sulfobromide phase. But let's say up to 200 degrees, it's all fine. So if you call that thermodynamically stable, I don't know.
Okay, thank you very much, Libero. We have one question from Sonia, but Sonia, as you're here, and I think that you have the possibility to ask yourself to please go ahead.
Yeah, okay. Thanks for the impressive talk. My question was if you have ever tried to introduce this lead sulfur halide material that stabilizes the cesium lead iodide into a thin film to stabilize the thin film.
Yes, we are doing this with the group of Anna Maria Petrozza in Milan. Mm-hmm. I don't know, because my video is freezing all the time, but you can hear me, right?
Yes.
Okay, because the video keeps freezing. Yes, we are doing it. So far, the results are not exceptional, but we are trying very hard. Yes, because of course the idea would be that you have this chalcoylide, and then you would completely lock the whole film.
Yeah. So is the nanoparticles are soluble in DMF, or you have to deposit the nanoparticles on top of the film?
What we are doing now is to try to trigger the solubility in DMF, which we don't have right now. Mm-hmm. So right now what we are doing is first depositing the chalcoylide nanocrystals and then depositing the perovskite film on top. But this is not the best solution. The best would be to homogeneously dissolve them in DMF together with all the precursors of the perovskite film.
Yeah.
But
they don't serve as a nucleation growth points?
Yes. As we hope to nucleate the perovskite on top of the chalcoylide.
Okay, good luck with that.
So far it's not working.
Okay. Yeah, it seemed very promising.
Sorry, my video is freezing. Now I realize this. Anyway.
Yes.
Okay. Thank you, Liberato.
Thank you, Libero. I have one question. I think I would love to debate it, but I think it's not the right moment and the right situation. You're coming from nanocrystals, from cat selenide, zinc sulfide, all of these core shell, and you did amazingly shapes and anisotropies with this kind of what I call classical semiconductors. So now you move to perovskites, and it seems that there are a lot of things that they can be translated. So all of this ligand exchange, of this cation exchange, all of these chemical transformations at the nanoscale, they can be, I would not say directly, but you can just translate the know-how from one particle or one kind of system to the other. But on the other side, I saw that regarding the formation of the heterostructures of the...
That's a very tough thing.
That's
the most difficult thing. And the problem is that many of the conditions that you would use to grow heterostructures in the standard colloidal synthesis would destroy the perovskite nanocrystals. Okay.
I see.
So you have to play around the tricks. One trick is, for example, to use these clusters. So we have these tiny clusters of perovskite, which actually we have a JAX paper coming out where we somehow solve the structure of these clusters and the shape. They are not really clusters, they are tiny disks. They're very tiny disks of basically one monolayer perovskite disks with 10, 15 nanometers in diameter. Somehow, if you use these clusters together with the precursor of the chalcoylide, you're able to grow the heterostructure. If you use the preformed nanocrystals of perovskites and you try to grow an heterostructure, so you could try to grow the chalcoylide, it doesn't work. And you end up also destroying the perovskite. Another way to make heterostructure, I have shown at the beginning of the talk, is starting, for example, from cesium bromide nanocrystals, and then react them with some reagents. So slowly trigger the formation of, well, in that case would be not very interesting heterostructure because the cesium bromide would be at the core. But maybe you can open some indiffusion of the atoms, the ions, and nucleate some core of a material inside the matrix of cesium bromide, for example. There are some other tricks, which is like, for example, controlled formation of phase transition. So Pei Dong Yang makes a film of cesium tin bromide in one phase, and then it triggers by a local heating transition in just one section of the wire. So you end up with a PN junction of a tin bromide, and the junction is between the two cesium tin bromide, but with different crystal structure. And one material behaves like a p-type semiconductor, and the other material says an n-type. So you have to play with a lot of ingenuity to try to figure out, how to make heterostructure. But this is indeed one of the futures, no? So you want to make perovskite, you want to make metal halide. Unless you make heterostructures, and so you start forming all these PN junctions, which would be good for catalysis, or type 1 structure in which the carriers are really localized in the core and they are stable. Unless you are not able to do all this, then all this chemistry is still primitive if you compare it with that of standard semiconductors, where you can make core shells, onions, you can make all this elaborate structure with quantum field, basically 100%. You can put them in TV displays. They work for years. And in perovskite, we are not there.
But do you think that it will be achievable? The only point is that we need the time to develop the synthetic strategies leading to this kind of structure.
Yes, you need to develop a lot of the synthetic strategy. You will have to fight against the instability. But I believe that a great part of this structural instability will be solved if you interface your perovskite, for example, with something that prevents a phase transition of that perovskite. So it will increase, for example, the potential for oxidation of tin ions, for example. If you are interfacing a cesium tin 2 plus kind of perovskite with another material, maybe because you would need to oxidize the tin and also to cause a phase transition to change the structure and composition of the cesium tin iodide domain, for example.
So sort of sacrificial, I would not say template, but a sacrificial layer on top of which you could nucleate a second or third material.
That is also another way to go, yeah.
We have one new question from the audience, from Kennedy Yaba, I'm sorry. Thank you, very interesting talks. A quick question for Sonia. This is for Sonia, not for Liber, I'm sorry. What is the thickness electrodes deposited? Was there any significant difference in charge extraction from different thicknesses?
Thanks, Kennedy, for the question. Actually, the thickness, well, it depends on the configuration, but for the gold, for example, we use the same thickness as we use for the perovskite solar cells, which is like 60, 80 nanometers. I think the thickness was changed, but there was not much difference on the charge extraction because the gold electrode just served as like metal contacts. And the extra molecules adhered in the bigger thickness didn't affect much the charge extraction. And also for the ones with the semiconductors, I remember the thickness that really affected the charge extraction was the insulating material that's between the nickel and the TiO2. And I think in the paper that was optimized, and 300 nanometers was the optimized thickness.
Okay.
Yeah.
Thank you very much. I think that the question is answered. If not, just Jordi Riol have a question to Libero and say, from an electron microscopist to the material scientist, what would you dream to have or what would you need as ultimate characterization? I'm sorry, there are coming a lot of questions. As an ultimate characterization tool for your materials. What do you want, Libero? Jordi has
it. One issue is, of course, the electron sensibility of this material. So as soon as you start looking at them, they degrade because, halide get easily dissolved under the vacuum, under the electron bombardment. So, the idea would be, I don't know, some sort of microscopy where the beam damage is very low, even in perovskites, in metal halides in general. And of course, another thing that I would like to acquire is, or would like to test the capabilities is, set up to do cathodoluminescence with the resolution in the TM, so that I can see, for example, light emission from a single domain of these heterostructures. I'm not sure that with the cathodoluminescence setups that, it's possible to acquire with the in TM. Right now, this is possible to have a resolution of just, 1 nanometer or so. I think maybe that's very difficult. I don't know.
Jordi says direct electron detect. You're reading the okay.
To avoid the damage, yeah, that could be one way to go. Yeah. We should talk with Jordi and Sarah Bals and other microscopists to maybe brainstorm on this.
We have one more question, and I think it would be, well, I would stay all evening discussing on the synthesis and the different strategies and the different important things. First, from Pin Peng Zhang again. I think that you can read it, Libero, right? All of us, we can read it, but this question is related to the cesium sublattice. I think that all of us can read the question, so if you can answer.
Which one is the one on the cesium?
Yeah, so
okay.
let me show. I saw your perspective before the
okay.
perovskites are related on cesium sublattice. For the case of cesium lead.
Yeah, in that case, is the lead sublattice that keeps everything on hold. Also, because in the chalcohalide perovskite there is no cesium sublattice, so it's the lead in that case that guarantees the continuity.
Okay, great. And we have one other call from Anna Roach.
The molten salt.
Hello, Anna. By the way, so
in this molten salt approach,
yes.
So we are not really the first to do this molten salt approach. What we did was to use a combination of salts, so that the synthesis can be done at 350 degrees instead of 700. So at 360 degrees with a specific combination of molten salts, we obtain not only the growth of perovskites into the pores, but also the collapse of the pores. So what you're doing is basically completely isolating the perovskite inside the pore. So the tricky part is to cause this collapse of the pore. You're partially fusing this silica at the surface so that everything gets shut down for the nanocrystals without going to temperature that would be prohibitive in the lab, 700 degrees. Now, 350 is more manageable. The quality of these nanocrystals is actually generally high. Actually, in the pores, you're not only crystallizing nanocrystals, but you end up with other salts, for example, potassium bromide. You form also other salts inside. And the crystals seem to be stable to high flux and high temperature. So high flux irradiation and high temperature. Some samples better than others, depending on the salt condition, and we are still optimizing them. What we are doing right now when we are preparing a story on it is to make silica beads, which are 100, 200 nanometers in diameter. We cook them in molten salt. We grow the nanocrystals in them, and we coat them with particles, with surfactants.
Liberato, just to finish with your talk, I think that everybody is asking or may ask you the same question, but I need to I need to ask you not about the toxicity of PV and so on and so forth, but about the sustainability of the material. I mean, I leave aside the toxicity of the particles that you are producing, but I think that you're working with molten salts, you are working with toluene, you are working with a lot of, let's say, non-green chemicals. So my point is that, is it feasible to scale up the synthesis? Because if you want to go to a final applicability, it doesn't matter. So whatever things that you want to do with the particle, you will need to scale up.
Yes, so that's why we are moving to these beads of silica, no, and use them and fill them with metal halides in general, not only perovskite, and use molten salts, because the molten salt environment does, I mean, you're cooking some salts, you're not releasing vapors, and you're not using toxic solvents. And when you're done with the synthesis, you just dissolve everything in water. So all the salts get dissolved in water. You end up with the silica beads. And then you can coat the surface of these beads with the ligands, and you can get them stable. And so these steps are much more environmentally green. And we are actually also trying to move away from the lead-based perovskites and try to grow something else in the beads. But I think I'm saying too much if this is recorded and posted.
No, I mean, I think it's okay. Yeah, I think it's very, very, very interesting on the things that.
But you also see we are trying to move away from the lead, at least from the materials point of view, exploratory materials. From the point of view of the interfaces and the heterostructures, we are still on lead because these systems are easier to study. Are more are better understood. But we are struggling, and what I've shown in this talk, it's only a few composition of lead-free materials. We have many others, which I have not had the time to report because they kind of, lead to a bit of different story and maybe too much spectroscopy for my taste.
Indeed, I'm very happy to see that you are working with heterostructures, because I saw a perspective that you and Maxime, you had a couple of years or 2 or 3 years ago about how difficult it is to I think in natural materials, how difficult it is to compose, to create this kind of heterostructures. And I think if there is somebody who can do it, is Liberato.
But there are many groups in the world that are doing very good work. Peidong Yang,
yes,
in the US, Narayan Pradhan in India is also trying very hard to make heterostructure. There are other groups in China as well.
Absolutely, absolutely. So Libero, thank you again very, very, very much for your time and your amazing talk. At some point we are here, you are in Italy.
Well, thank you also to Sonia for her amazing talk.
Yes, yes. to you and to Sonia. I think that the results that you present, they are completely outstanding. And thank you very much to all of the audience to share our time, to share their time with us, and to spend quite a wonderful afternoon, evening of nanocrystals and things that we can do. Libero, thank you very much. Sonia,
thank you for the invitation, and have a good evening.
Have a good evening. Thank you for your attention. Bye.
Bye.